Alright, this next section is 4.3, and it's called Writing Functions. And I'm going to start out with a Roman numeral 1, and just want to kind of cover what are independent variables and dependent variables. Independent and dependent variables. And you might have gone over these in like a science class or something like that, but typically in math class, your x value is going to be your independent variable, and your y is going to be your dependent variable. Now sometimes those will have different letters like speed and distance or something like that, but for all those you should be able to go and say, if you're trying to figure out which one's which, like blank depends on blank. And then if you take those two things and switch them back and forth, usually it'll make more sense one way than the other. Sometimes it'll kind of make sense both ways, but one will involve a conscious choice. Then you want the one where no choice is needed. So once you do that, this will be your dependent variable. And this one here will be your independent. And we'll do a couple examples. I think that'll really kind of help things make sense if we do a few examples. So I'm going to go with my first one being something like this. So we're talking about the winter gas bill. So how much money the gas company charges you to heat your house. So the bill and the outside temperature. So if we were to take, you could write it one of two ways. You could first say your bill depends on the temperature. And that kind of makes sense. The bill would naturally depend on the temperature. If your temperature is colder outside, then your bill is going to be higher. Or if the temperature is warm outside, if you live where it's 65 for Lowe's, then your bill for your gas company is going to be pretty low. If we were to try those in the other order, then we'd say your temperature depends on your bill. That doesn't make sense. It doesn't mean that if you get charged a lot of money, then suddenly it's going to be colder outside. So it has to be that first way then. So the one that we like, the bill, that is going to be the dependent variable, so that's the dependent. And the temperature is going to be the independent. If we were to jump and do a second example, we could do something like, let's say the length of showers. So the length of your shower and the water bill. So now we have a length of the shower and the water bill. So you could say the length depends on the bill, or if we were to try switching those around the other way, your bill depends on the length of the shower. Now, this is one of those examples where they both kind of make sense to me. This first one, the length of your shower depends on your bill. Well, that makes sense. If the water costs a lot, then you're going to take a shorter shower because you're cheap. At least I'm cheap. Where the second one, the amount of money in your water bill depends on the length of your showers. Well, yeah, that happens too. So the one that we keep, though, is going to be this bottom one. The bill just kind of naturally depends on the length of your showers. That one, it doesn't have any conscious choice, it just naturally works that way. This first one, the length depends on your bill. Well, that's like at my in-laws' house, their water is way more expensive than here because they just redid their whole water system in Scottville. So you would choose to take a shorter shower because you know it's going to cost a lot of money. So in this case then, the bill is going to be the dependent, so that's my dependent. And the length, that's going to be the independent. One last example, and then I'll kind of move on. I'll try to do this one quick, but we're looking at the time knitting and the length of a scarf. So you have the time and the length. And I'm not going to write the whole thing out. Maybe you can skip writing if you want to, but does the time you knit depend on the length, or does the length depend on the time? And I would say that it's that second way. The length depends on the time. So the length then would be my dependent, and time would be my independent. Because the length naturally depends on the time. The more time you knit, the longer your scarf is going to be. Okay, so we're going to move on to Roman numeral 2 then. and we're going to do something called function notation. So function notation. It's something that you're going to see popping up more and more and more as you go. But sometimes they'll make it a little confusing in how they write the thing out. So I'm going to start out just by saying this here. And this would be something that you can kind of refer back to if you get a question that messes you up, where they'll say the dependent variable. And we said at the very beginning that the dependent variable is typically going to be a y if you have an x and a y, but it could be different letters, like we just looked at. The bill depends on things, and the length of a scarf depends on things. So you could have an L for that length of a scarf, depends on the time. But they'll say the dependent variable is a function of the independent variable. And the independent variable, if you have an x and a y, tends to be your x value. Now, when you see this and it's confusing, they're going to be putting in things other than this, the dependent variable and the independent variable. Instead, they'll say something like the length of a scarf is a function of the time you spend knitting. And when they do that, when they say for this first part, the length of the scarf is a function of the time you spend knitting, now you know that the length of the scarf is going to be the dependent variable and the time is going to be the independent variable. So as we go through and write these things, the equations are usually going to be something like y equals something over here with an x. Or you could have different letters in there too, but typically you're going to have one variable equals something. And this variable over here that's by itself is going to be the variable for this dependent variable. So in this example, it would have been like a L for the length of a scarf. Now this new thing that we're looking at, called function notation, is going to be where instead of a y, they replace it with something like a f of x. And there's nothing special about f. Sometimes you'll see like a g of x, or an h of x, or a q of x, or something like that. But there's going to be some letter, and then the parentheses, and then another letter inside the parentheses. And also for f of x isn't always the same equation. In one problem, you may get f of x equals 3x. Another one might be f of x is x plus 2. So it's not like you need to memorize some fancy equation. But this here is called function notation. And really the whole key, and you might want to like put this in a different color for dramatic emphasis, is it's really just a fancy way of writing y equals. So function notation, it's really just a fancy way of saying y. And if you keep that in mind, when you see something like the f of x or the g of x, it's going to make a whole lot more sense if you just look at it as though, okay, really, that's just kind of like a y value. Let's do a couple examples with this. I think that'll help kind of clear the air a little bit. But maybe we'll have something like, they start out by giving you an equation. So they'll say f of x equals 3x. So for this problem, f of x is kind of defined as being 3 times x. The book is going to start out trying to make it a little bit easier, and they'll say find f of x when x equals 8. Soon, instead of saying find f of x when x equals 8, they're just going to write it this way here. So I figured I'd show it to you right now and just start doing it this way right away. They're going to say find f of 8. And if you think about it, that should hopefully make sense, because here they're saying find f of x, but then they tell you x is 8, so we could just substitute an 8 in for x, which would give us this f of 8. But if I take this f of 8 right here, that kind of lines up with my problem right here. And if you see that, well, you could see, well, we want to find f of x. X is just that variable. We know the variable equals 8. So now over here on the right-hand side, I can just replace my x with 8 because we know x equals 8. And 3 times 8 is 24. So in other words, what we really just found is y equals 24. But instead they're writing y as this whole f of 8. But anyways, the point is if you wanted to look at this as a point, you know the x value is 8, the y value then would be 24 for that x value. So I'm going to, in red for dramatic emphasis, really the key to doing these function notation ones is you'll always just replace the variable with what's in the parentheses. Because they're going to take that independent variable and put it inside the parentheses when they give you this function notation here. So if we know this is the independent variable, and they tell us what the independent variable is, well then you would just put that independent variable in for x, or put that number in for x. I'm going to go and do another example or two. So if we stick with that same f of x is 3x, well then I could say, so I'm kind of going to this equation right up there. So if we know f of x is 3x, and they tell us, alright, find f of 12, well then we just do 3 times 12. You take what's in that inside the parentheses, you replace your variable with it, and you get an answer of 36. So the point then would be 12, 36. When x is 12, y is going to be 36. And like I said before, there's not really anything special about that equation, that you could get a totally different one. So example 2, but maybe now they'll say, alright, f of x, that's now going to be a 2x minus 4. And if they say, find f of x when x is 7, or if they go on and just say, find f of 7, you do that same exact thing as before, that your x is really just 7, so you're going to take your 7 and put it right in there for x. So I have a 2 times 7 minus 4. With order of operations, we have to multiply first, so we get a final answer of 10. So in other words, you could say f of 7 is 10, or look at it as though when my x value is 7, my y value is 10. We're getting close to being done. Just want to throw a couple more things at you, make sure we're all on the same page. Maybe for another example, this would be like example 3 or something, we'll say g of x now. So we're using a different letter than f. And g of x is defined as being x minus 4. And maybe the question will say find g of 17. So you take whatever's in that parentheses and you're going to replace your variable with it, because we see here x is just going to be 17. So we put a 17 in over there for x. So we get a 17 minus 4 for 13. So you know then when your x value is 17, your y value is going to be 13. And typically you don't have to write it as a point like I'm doing there. Really, the answer is just g of 17 equals 13. But I'm just trying to show that this here is the y value for that x value. It's kind of what I'm trying to get at. Very last example, you might see something like this. So write an equation to fit the data table, or fit the data, but we want to do it in function notation. And maybe you'll get a data table that looks something like this here. So I'm just going to quick whip one down, and I'm going to say here's my x, this is my y, although I'm going to change my y in just a minute. So I have the 0.18, another 0.211, third point is going to be 314, and last I have 7 and 26 for my last x and y. Alright, so now if we're looking at these, the way I encourage people to attack it was to say, alright, if we maybe go with something like this here. Alright, so we could get from 1 to 8 by adding 7, or we could get from 1 to 8 by multiplying by 8. We're hoping that that works for one of these next ones, or all these next ones. So if I were to do a 2 plus 7, that gives me 9. So it looks like this can't be it. And then hopefully we could do, alright, well it's 2 times 8, well that's 16, so it's not going to be either of these. So we know that we can't do it with the short, easy way. So instead we have to say, alright, when x goes up by 1, hopefully these go up by a constant amount. So I have a plus 1, a plus 1, so I have a plus 3 and a plus 3. So it looks like every time x goes up by 1, y goes up by 3. So we could start out saying y equals 3x. Because that's going to give me an increase of 3 for y every time you have an increase of 1 for x. Now the problem is that doesn't fit my point. If I were to do 3 times 1, it doesn't give me 8, it gives me 3. What do I have to do to the 3 to get up to 8? Well, 3 plus 5 gives me 8, so hopefully I can put a plus 5 here, and that'll work now for all my points. So I could say, alright, well, when my x is 2, I could put a 2 in there. 3 times 2 gives me 6, plus 5, sure enough we get the 11. Or when x is 3, 3 times 3 is 9. I put a 3 in there. 9 plus 5 is 14. And when x is 7, 3 times 7, 21, plus 5, I get my 26. So we know now that this here is my equation. So I can say, alright, that's my answer, but they give us this in-function notation. So in other words, we can't write it this way, where we have y equals 3x plus 5. And sometimes they'll actually go through and they'll label, instead of an x and a y, they'll say, well, we said that f of x, or g of x, or h of x, but something like this f of x here is going to be a fancy way of saying y. And they would have given you this f of x in the original equation. But all that you do is replace the y with your f of x, or g of x, or whatever they said. Then you have 3x plus 5. So that there would be your final answer. Final comment, I know the notes are getting kind of long, but this guy here is going to be the guy that really kind of came up with this notation, and his name is spelled this way. And a lot of times people call it Euler's notation, but that's actually not how you pronounce his name. I was corrected by my nephew, but his name is Leonhard Euler. But so if you see like a Euler's notation or Euler's notation maybe, that's kind of what they're referring to, this whole thing with f of x or g of x.